In this video, we'll look at some rather interesting and useful properties of complex conjugates. Firstly, we'll just look at some basic arithmetic. Thanks to symmetry, adding z with its conjugate means that the imaginary parts cancel out and just leave us twice the real part of z. Similarly for subtraction, the real parts cancel out, just leaving us twice the imaginary part times I. Multiplying z by its conjugate, again thanks to symmetry, results in a difference of two squares, and we're just left with a squared plus b squared, which hopefully from an earlier video we recognise as the modulus of z squared. Now we'll demonstrate that conjugation is commutative. We'll consider addition and multiplication, and subtraction and division can be left as an exercise. Let's consider z plus w conjugate first, using our usual rules for addition. Add the real parts, add the imaginary parts, and pull out the common factor of I. And then in the final step, we'll take the conjugate, which just switches the sign of the imaginary part. Now we'll consider z conjugate plus w conjugate. So we'll take the conjugates of the complex numbers first, and then we'll add them using our usual rules of addition. And as you can see, the result is exactly the same as z plus w conjugate. Now we'll consider multiplication. So we'll consider zw conjugate first, which means we need to multiply the two complex numbers first, then take the conjugate. And the conjugation step again just switches the sign of the imaginary part. Now let's look at z conjugate times w conjugate, which means we take the conjugates first, and then we multiply. And as you can see, again we get the same result as zw conjugate. Now we want to demonstrate that the conjugate of the conjugate is just the complex number itself. Seems like a rather obvious result, but we'll use it shortly. Now let's consider the reciprocal of z. So we'll write 1 over z as 1 over a plus ib. And we know for division, we multiply the numerator and the denominator by the conjugate. And on simplification, we can see that the numerator now is a minus ib, which is z bar. And on the bottom, we get a squared plus b squared. And we've only just established that a squared plus b squared is in fact the modulus of z squared. This is a result that's surprisingly useful in trigonometry, but we'll see that in a future video. Now another obvious statement, but it's rather important and we'll use it shortly. The modulus of the real part of z is less than or equal to the modulus of z itself. So let's go through and demonstrate this. The modulus of the real part of z, well that's just the modulus of a, because we define z to be a plus ib, but the modulus of a is just the square root of a squared, but this is clearly less than or equal to the square root of a squared plus b squared, as long as we're assuming there is actually an imaginary part, and that's equal to mod z. Now let's use all this to prove a rather important result, which you can see here, known as the triangle inequality. We'll only prove the right-handmost piece, that the modulus of z plus w is less than or equal to the modulus of z plus the modulus of w. It's known as the triangle inequality, because as you can see from the picture here, it's talking about the lengths of the sides of a triangle. But we're going to demonstrate it using properties of conjugates, just so that you can see how powerful these conjugate results are. We'll start with the square of the modulus of z plus w, which by rule 3 we can just see is the product of z plus w and z plus w conjugate. Then we can break that second bracketed term up, the conjugate, into conjugate pieces and simply expand that out. Then by rule 3, zz conjugate is the modulus of z squared, and ww conjugate is the modulus of w squared. And by rule 8, zw conjugate is the conjugate of z conjugate w. And we did this because now we can employ rule 1, that wz bar plus bar of z bar w is twice the real part of wz bar. But then since this is a real number, it's just equal to its own modulus, and then we can employ rule 10 to get our inequality. But then since the modulus of a complex number and its conjugate are the same thing, the modulus of wz bar is just the modulus of w times the modulus of z. Finally, this is a perfect square, and hence we get our result. In the next video, we'll look at properties of quadratic equations involving complex numbers and generalize that to polynomials.